There are a lot of formulas associated with waves, so you want to feel comfortable with what each variable represents. First, this is the general equation of any oscillating wave. Because it's oscillating, we can use sine or cosine, depending on if we want the zero position to be a maximum or zero. A describes the amplitude of the wave, or the maximum displacement from rest. K represents the wave number of the wave, and we'll explore that in a moment. Omega represents the frequency of time propagation of the wave, and phi represents the phase shift. This phase shift allows us to horizontally move our wave in time and space to fit whatever thing we're observing. Notice that there's a negative sign in front of omega. This is the convention we use to describe a wave propagating in the positive direction, which in most cases is to the right. As you know, we can define the speed of a wave as the frequency times the wavelength. However, we can also relate frequency to its rotational analog, omega. Omega is just equal to 2 pi times f. Moreover, we can define a wave number k that is just 2 pi divided by lambda. So using these two relationships, plugging back into our velocity for a wave, we end up with a new relationship between velocity, omega, and wave number that we can get directly from our equation. Now we also know that the speed of a wave will depend on the medium it's in. For light, we saw that the speed depended on the index of refraction. If we have a wave that's moving in a string, it depends on how taut the string is, so we look at tension as a unit of newtons, and here this is mu, which is a representation of the mass per unit length of our string. So really thick strings will have a high mu. We can also look at sound in a fluid. How fast will sound waves move? In the case of this equation, B refers to a bulk modulus, which is a representation of how compressible a fluid is. Rho refers to density, or how dense that fluid is. So you may have heard that water actually has sound waves that travel faster than in air. And that's because even though water is more dense, it actually has a much bigger bulk modulus to compensate for it.